Hello. Welcome to Backer Breaks It Down. In today's episode, we're going to simplify some trig expressions. Ooh. What does that mean? All right, so let's start with the fundamental identities. Trig identities are equations that are true for all real numbers for which trig expressions in the equations are defined. Okay, what does that mean? Well, some of them we already know. Like we know the reciprocal trig functions, that sine is 1 over cosecant and cosecant is 1 over sine. And we know that cosine and secant are reciprocal functions, and tangent and cotangent are as well. Furthermore, tangent and cotangent, I don't know if you've ever realized this, but tangent is sine divided by cosine, which means cotangent is cosine divided by sine. So I'm going to let you know something. When it comes to tangent and cotangent, very rarely do we actually use these two. Like, it's so much more useful to use that tangent is sine over cosine and that cotangent is cosine over sine. So much more useful. Okay. And then we have our Pythagorean identities. Okay. And so there's 3 of them. So we have sine squared plus cosine squared is 1. 1 plus cotangent squared is cosecant squared. And 1 plus tangent squared is secant squared. Okay. You also have these odd even identities. And so the only time you would ever use an odd even identity is when you have a negative angle. See this? So if you ever have a negative inside like that, then you must use an odd even identity to rewrite it because we want all of our angles to be positive angles, okay? So if you encounter sign of negative angle measure, rewrite it as negative sign of a positive angle measure, okay? And so on. So when we simplify trig expressions, we're going to substitute using identities. One big and very useful strategy is this one here. Rewrite the expression in terms of sine and cosine. Because you can rewrite tangent and cotangent in terms of sine and cosine. You can rewrite cosecant in terms of sine and secant in terms of cosine. So that is a really useful strategy. There are some other strategies that may come into play, like factoring. We'll see an example of that, I think, in the next video. But that can happen. It might be possible to combine a sum or a difference into a single expression, or to rewrite division as multiplication. That's just multiplied by the reciprocal. Okay. You've got some other useful pointers in your notes. This is how you multiply fractions. You simply multiply the numerators together and the denominators together. Canceling, you can cancel out things that appear in both the numerator and the denominator. And dividing fractions. When dividing fractions, rewrite the top fraction and then multiply by the reciprocal of the bottom fraction. So they're showing you 7/9 divided by 3/5 is 7/9 times 5/3. So they're multiplying by the reciprocal to get their answer because it's a lot easier to multiply fractions. Okay. You might have to simplify a complex fraction. To do that, you simply multiply by the common denominator. So look at all the mini denominators and decide what is the common denominator. So here you've got x squared, x, and 6. Put all those together, you get 6x squared. That's the common denominator that you then multiply everything by. Okay, but these are just things that are going to pop up. Not always, but could pop up in these problems. Okay. So let me take you through the examples that we have in our notes. Rewrite each expression by changing to sines and cosines and simplifying the resulting expression. So taking a look at number 1, I've got cosecant tangent of negative alpha. Gotta deal with this. Can't leave that negative angle measure. So remember, tangent of a negative angle is equal to negative tangent of x. And you'll notice that's the first thing that I did was I used an odd even identity to rewrite tangent of negative alpha as negative tangent alpha. Okay. So the next thing I'm going to do is I'm going to change to sines and cosines. So cosecant can be written as 1 over sine, and the negative tangent can be rewritten as negative sine over cosine. So notice that I've got a sine on the bottom and a sine on the top. Those signs are going to cancel each other out. That's why I'm crossing them out here. So then what remains is negative 1 on top, cosine on the bottom, and that is just negative secant. And that is my simplified answer. So let's take a look at another example. We have secant omega times cosecant omega times cosine omega. Omega is our angle. It's a Greek letter. It looks cute. So we're going to do the same thing. We are going to change to sines and cosines because that is such a useful strategy. So that's what I did. Okay. I rewrote secant as 1 over cosine, cosecant as 1 over sine, and cosine didn't need to be rewritten at all. So then I noticed, hey, there's a cosine on top and a cosine on the bottom. You know what that means. They cancel out. And so what I'm left with is 1 over sine, which is simply cosecant omega, and that's my final answer. So let's take a look at one more before we go making things a little bit more challenging, because this really hasn't been that bad. We are simply changing to sines and cosines. So sine and cosine aren't going to change, but I can totally change tangent into sine over cosine, because that is a very, very common, changing things into sine and cosine. You definitely want to use that tangent as sine over cosine. So then if you look at what we have division. We have sine beta cosine beta divided by sine beta over cosine beta. So when you're dividing with fractions, do the same change flip. Keep the top the same. Flip the bottom. So sine over cosine became cosine over sine. And then notice there's a sine on top and there's a sine on the bottom. So these signs, they cancel each other out. So what am I left with? Cosine squared. And so I'm going to end this video here. If you want to see examples 4, 5, and 6, you should check out the next video. But writing things in terms of sine and cosine, this is an extremely useful strategy that if you're at a loss of where to even start by doing that. And that's how Backer breaks it down.